Welcome to this 7th lecture in the Structural Dynamics course. Today we're actually going to jump to one of the most important topics. So this lecture and the next lecture will be quite important to perform dynamic analysis, also in the industry when you have to solve problems there. It's called modal analysis, and the idea is to actually represent the dynamics of the structure by its inherent vibration forms. So therefore we will split the topic into two. Today we will consider these particular vibration forms. We'll call them mode shapes, and they are found as eigenvectors to an eigenvalue problem. The corresponding eigenvalues to this eigenvalue problem are then the natural frequencies. So therefore we'll consider the basic idea and matrix formulations today, and next time we'll then use these results to actually set up the implementation and consider a little bit about system reduction. So first of all, we will consider the equation of motion. And for everything today, we will have undamped free vibrations. So we will have the unloaded equation of motion, whereby we will find solutions that satisfy an eigenvalue problem. I'll get back to that. For this eigenvalue problem, we will, in bullet number 3, consider eigenfrequencies and undamped mode shapes. And quite importantly, these mode shapes, they obey so-called orthogonality conditions. We will derive the mathematics behind it, but what is important is that we get modal mass and modal stiffness. Quite extensive example considering the vibration of a cable, because for this particular structure we can actually come up with analytical solutions. That's nice from an academic point of view, maybe less important in real life, but anyway we will consider the results, and finally, if time allows, we can come up with the so-called Rayleighs quotient, which is a nice way to actually estimate the first natural frequency for a structure if you do not want to calculate the full eigenvalue problem. Let's just recapture last lecture's main results for the finite element method, because everything today will set up for a discretized system underlying the finite element method. So consider the a 5-node structure as given here. It's a beam structure, and for each node we will have a transverse degree of freedom and a rotational degree of freedom. So for 5 nodes we will have 10 degrees of freedom. Let's actually go to the bottom of this slide, because on the left hand side of the figure you can see simply supports at the first and last node. That means that Q1 is actually restrained by the support, and Q9 is also restrained. So let me just mark these two with green. So Q1 and Q9 are actually supported, and that leaves us with 8 free degrees of freedom. Those are 2 to 8 and Q10. Those we collect in a single column vector Q, that's our solution vector, and in the general equation of motion we will have 3 terms. We'll have the inertia term that contains the mass matrix M, we'll have the stiffness term containing the stiffness matrix K, and one intermediate term that represents damping. We will today omit any damping terms and consider that in the next lecture. Any loading is then assembled in a column array or column vector that appears on the right hand side of the equation of motion. Also today we will neglect any loading and only consider free vibrations. Those free vibrations can then be initiated by initial conditions. That means at time equal to 0 we could have some initial displacement and some initial velocity. So that's the idea of today, and what we will mainly focus on is then the solution of the governing equation, where we have free vibrations. That means there's no loading on the right hand side, and undamped vibrations. That means that the damping term is omitted, assuming a vanishing damping matrix. I would like to jump directly to such a simple structure, discretized structure. Either we can, on the left, as indicated on the left hand side of the figure, we can consider a structure with 2 masses, M1 and M2, supported by 2 springs, K1 and K2, and in the figure they're represented as X1, X2. Just to get the notation right, let's assume these as Q1 and Q2. So in the figure simply replace in your mind X by Q so that we have consistency in the notation. The way we set up the equation of motion is that we one by one isolate each mass. Then we simply apply the forces acting on the masses. In this case, these forces from the springs. As there's no external loading and no damping, then only restoring spring forces appear on the structure. So if we want equilibrium for, let's say, mass number 1, we will have mass times acceleration for the first mass, and if we look at the first mass, I'll just underline that in red. Here we see that we have a contribution from the left spring. It works with a minus in the right hand direction, and therefore it appears with a minus on the right hand side of Newton's second law. And we also have a contribution from the right spring, and it also works in the right direction if we denote Q2, that means x2 in figure, before Q1, that's x1. And that provides us with this expression here. Then we set up the similar equation of motion for mass 2, it's given here, and then we can combine these two expressions into two equations with two unknowns, Q1 and Q2. And the general principle of such a system of equation is, of course, that we will have the sum of inertial forces plus and the spring forces, and they should be in balance and therefore equal to 0, in this case in a so-called matrix sense. And this matrix sense or matrix representation is then indicated on the next slide. First of all, we organize all our degrees of freedom, in this case Q1 and Q2, in this column boldface Q vector. Of course, the organization of the matrices and in basically the equations is entirely decided on the order that you choose for in this vector. And in our case, the obvious choice is that Q1 is the first component and Q2 is the second component. The corresponding accelerations are then given in the boldface Q double dot vector, simply the time derivative of the vectors. Of course, all the math differentiations for individual Q components is also valid for its governing vector. Then, if we go back to the equation of motion, we see that the accelerations are multiplied with masses. So, if we go back, they appear in a diagonal matrix. That means we will also have a diagonal mass matrix, M1 and M2, organized in the mass matrix boldface M, while the stiffnesses appear with positive values in the diagonal and negative values in the off diagonal. And that is also what we see in the corresponding stiffness matrix. If you, by any chance, will get negative diagonal elements, you will, for mechanical systems, have made a mistake, because the diagonal elements are the direct stiffnesses. So if a certain mass is moving to the right, the stiffness will always provide a force in the opposite direction. Positive entries in the diagonal. So it's always a good check. Furthermore, stiffness matrix will, in terms of energy, always be symmetric. So never formulate a non-diagonal stiffness matrix. If it, in your formulation, becomes non-symmetric, then always find another way to write the equations so that you re-establish a symmetric stiffness matrix. And the same thing will hold then for the mass matrix. If we then introduce these matrices and vectors into the equation of motion in 7.12 at the bottom of the previous slide as shown here, well, we can write this in general and compact matrix vector notation as mass matrix times acceleration vector plus stiffness matrix times displacement vector equal to 0. So this is just an assembly of all our equations of motion. And the corresponding initial conditions that we could use to initiate vibrations in our structure are then also directly formulated in terms of Q at time equal to 0 and Q dot at time equal to 0. So, as referred or mentioned at the bottom of this slide, we have a general matrix formulation, of course not only valid for a 2-degree of freedom system, but for a general multi-degree of freedom system. And this multi-degree of freedom system is then referred to as an M-DOF system. Or in our case, in our special case, it's just a 2-DOF system. But multiple DOFs is the extension we're looking for compared to the, or relative to the previous case we've considered with a single degree of freedom system, an S-DOF system. And because we have no loading on our structure, we will consider free vibrations today. As you might remember from solution of ordinary differential equations, the solution is often sought for complex exponential functions. And this is actually also applicable in our case, where the dynamic solution is then assumed in a separated format with a amplitude vector u and a temporal exponential function with the exponential function containing the argument I omega t. Omega is, as we note, an angular frequency, while t is time. And the corresponding amplitude vector then contains amplitudes for each of the degrees of freedom, and we refer to this as the vibration shape, or, in a moment, the mode shape vector. Although we are not entirely there yet, but it will be. So let's put it like this. Again, like we have for the single degree of freedom system, when we introduce the full complex solution, we actually imply that the actual solution, the physical solution, will then be the real part of Q, which for real values of U then introduces the harmonic cosine function. And that's the reasoning behind introducing the exponential function, is that it, behind the scenes, actually represents harmonics. Let us take the solution in 7.17, our expression, and substitute into the equation of motion in 7.15. So that means we will get a mass matrix, and then we will get the double derivative of Q. Let's just write that up here. The double derivative will then be I omega squared u e I omega t, or simply minus omega squared exponential function I omega t. I'll introduce this here, and I seem to have forgotten a u in here. Plus the stiffness matrix, and then just u exponential function I omega t equal to 0. So we immediately identify that the exponential function is a common factor on both terms. So is u. So therefore, both the u and the exponential function can be placed outside the parenthesis. Inside, we then reorder the two terms so that typically the stiffness matrix is written as the first entry or term, while the mass matrix times the angular frequency squared will then be the second term. And everything should be equal to 0. U cannot be equal to 0. If u is equal to 0, then q will as well be equal to 0, and that's a trivial solution. The complex function can never be equal to 0. So that means that what is inside the parenthesis must be equal to 0, and that provides us with the so-called eigenvalue problem, or in this case, because we have both a stiffness matrix and a mass matrix, we have a two-term eigenvalue problem, we refer to this as a generalized eigenvalue problem. Less important, although you want to have the mathematics right. So we are now looking for a particular case. We are looking for a solution to u that cannot be equal to 0, although we have a 0 on the right-hand side. You'll immediately see that u equal to 0 is a solution. But it is what we refer to as the trivial solution. So for non-trivial solutions, we actually require that the matrix here must be equal to 0. But when is a matrix equal to 0? So it's a set of equations that require, or that must be what we refer to as singular. That's the same thing in a matrix sense as for a scalar problem equal to 0. So a singular coefficient matrix means that the determinant of this matrix must be equal to 0, also sometimes written with these vertical bars. So an eigenvalue problem, at least in our sense with the structure and in dynamics, represents a set of equations of motion which have or which contain non-trivial solutions. There might be one, there might be many, there might be infinite non-trivial solutions, although the structure is unloaded. And we haven't used initial conditions or anything here. So it's just a set of solutions that tell us something about the structure without taking into account what particular loading we have on the structure. Let us go back to our simplest non-S-Dov structure. That is our 2 degree of freedom shear frame building or spring mass system with masses m1 and m2 contained in the mass matrix. So let's just remember that k minus omega squared mu equal to 0. For this 2-div system, we can actually write this explicitly as done in 721. So we have m1, m2, we have the eigenvector contained as u1 and u2, we have the eigenvalue, that's our angular frequency squared, and k1 and k2 occupy symmetrically the stiffness matrix K. So we take the difference between two matrices. That means we subtract the terms individually for each component. For the upper left, we will have k1, k2, and we will subtract omega squared m1. That's what we have here. Since the mass matrix is diagonal, we will have no contributions in the off diagonals from the mass matrix, and then it appears again in the bottom right diagonal element. So we then simply calculate the determinant of this 2x2 matrix. And a determinant for a 2x2 matrix means that you multiply the two diagonals and you then subtract the two off diagonals. So let's take a matrix A, B, C, D. That gives you AD minus CD. And this we do by this 2x2 matrix in 723. And when you rearrange things, you actually see that it can be written as done here in 724. What you might immediately see is that we have a term with power 4, term with power 2, and a constant term. That means we can actually write this as omega squared squared. This is already omega squared. So although it's up to the power of 4, mathematically speaking, it's just a quadratic equation. That means we can solve it in omega squared. The corresponding eigenvector that we have from 722 is then given by the two entries u1 and u2, and we'll have a look at that. We can actually find that once we've found our eigenvalues. So the omega is always the first thing we determine, and then we go back to 722, and we'll find a relation between u1 and u2. Let us, on the next slide, consider the simplest system. So m1 is equal to m, m2 is equal to m, k1 is equal to k, and k2 is also equal to k. We have q2 and q1. So that means we have equal mass and equal stiffness. In this particular case, the quadratic equation in omega squared becomes substantially simpler, and we normalize it by stiffness and introduce a reference stiffness, omega 0, so that we can write this in an extremely compact and non-dimensional form. Let's just have a look at omega 0. So omega 0 is not a frequency that actually appears for our structure. So omega 0 will be the natural frequency if we took one of the two stories in our shear frame building with m and k, and the natural frequency for this system, as we know basically from lecture number 1 in this course, will then be stiffness over mass, and if we take the square root of that. So that's just omega 0, simply introduced to get a non-dimensional frequency and thereby normalize our equation. Basically, it's not needed. The solution to a quadratic equation, you find the discriminant, and then you take minus the intermediate term and plus minus, as given here, the discriminant, and you divide by 2. That means we have two solutions for our omegas. We have omega 1 divided by omega 0, and we have omega 2 divided by omega 0. The first one is actually less than omega 0, whereas omega 2 will be larger than omega 0. That means for our, in this case, 2-degree of freedom structure, or for any general multi-degree of freedom system, we can actually find the natural frequencies for each vibration mode, for each eigensolution, by solving the eigenvalue problem. And in many cases, that's what you're looking for. You're often interested, for instance, for a pedestrian bridge. You will ask the question, how many modes have omegas smaller or less than 5 hertz? And remember that hertz is equal to radians per second divided by 2 pi. So these natural frequencies that we get from the eigenvalue problem, as the eigenvalues are often what we are initially looking for. But another solution that is quite interesting is, of course, the corresponding mode shape vector, the eigenvector of our problem. This eigenvector tells us something about how the structure will vibrate at a given natural frequency. So now we know omega. So we could, for instance, go back to our original eigenvalue problem here in 722, bring along this equation and write it in its simple form, and we could have a look at the first row, because the first row will be 2 minus omega, and let's say it's now omega, it could be omega 1 squared m, and it's definitely something wrong with the units. I need an m, k, sorry, there's a k missing here. That means I need let me just take the big eraser here and try again. So I'll have from the first equation 2k minus omega m u1 minus k u2 equal to 0. And from this equation we will actually find an expression between our system u1 and u2. Let's write u1 as function of u2. That would be k divided by 2k minus omega squared times m. So we know k, we know m, and now we can choose. Let me just take u2. So we can now substitute omega as either omega 1 or omega 2 to actually get a ratio between u1 and u2. This is actually done in expression 729, not for the top equation, but for the bottom equation. And when you look at these two expressions, you immediately see they generally look different. However, it doesn't matter whether you take the first or the second row in 728. Because the natural frequencies are eigenvalues to our matrix, these two solutions will qualitatively give the same result. Let's have a look at 729 again. And what you see is that when you substitute in and normalize this expression, it can be written as 1 minus the non-dimensional frequency squared. And the non-dimensional frequency we know from the previous slide at the bottom, which is either less than unity or somewhat larger than unity. So when we substitute this expression into 729, we find a relation or a ratio between the bottom story to the top story displacement that becomes less than unity for the first mode and negative with a value larger than unity for the second mode. How should we interpret this? Let's take the first mode, and that's shown to the left in the figure below. So let's assume that u2 is equal to 1. That is actually indicated here. So we assume a value for u2. From the upper equation in 730, we can then find that u1 will be equal to this value on the to the right of the equality sign, that is 0.618, as indicated in the figure. If I had used a value of 2 instead for u2, I would simply have doubled this value to something like 1.2, and then some additional decimals here. So somehow the solution to the eigenvector that we have here in 730 only defines the relative shape of the mode shape and not the magnitude of the deflection. So it only provides us with the ratio between u1 and u2. We don't get a value for u1 and a value for u2 that are fixed. They are related. So we choose either one of them and find the other. For the second mode shape, it actually turns out that the bottom story or the bottom floor has a larger deflection than the top floor, simply because that the minus 1.6, numerically speaking, is larger than 1. Therefore, let's do it the opposite way. Let's assume that u1, that's just an assumption, let's assume that u1 is equal to 1. We then plug that into the expression in 730, which will then give us that the u2 value will be minus 0.618. That means less than unity and negative. Thus, if we have a positive deflection to the right for the first floor, we will have a negative deflection in the opposite direction for the second floor. And here's an interesting thing that is valid for eigenvectors, for mode shapes. The lowest mode shape, if the lowest mode shape has zero deflection or zero crossing with equilibrium, then the next mode shape will have a single crossing with equilibrium. And if we had more degrees of freedom, the third mode shape would have 2 crossings, the fourth would have 3, and so on. So that's a nice property of eigenvectors. So what have we learned until now? Our assumption is always in this course that we have some kind of matrix formulation for the governing equations. We will introduce a complex exponential solution with an angular frequency and some kind of vibration amplitude referred to as the mode shape vector. When we substitute that into the equation of motion, we will, as indicated in 733, get an eigenvalue problem. So what we typically do is that we denote these eigenvalues and eigenvectors by an index j, and we will have just as many solutions to our eigenvalue problem as we have 3 degrees of freedom. That means once we have introduced our supports. If we do not introduce our supports, we will of course have more eigensolutions, but the frequencies for these eigensolutions will then just, additional eigensolutions, will then just be equal to 0 because they represent rigid body modes, the ability of the structure to actually move freely without deforming. So our eigensolutions consist of n eigenfrequencies, or natural frequencies, omega j, and the corresponding eigenvector uj, representing the mode shape vectors. So those, mathematically speaking, we can set up in these set of solutions where we know that, or we order them so that the lowest natural frequency is identified as omega 1, the second lowest is omega 2, all the way up to omega n, which is then the highest natural frequency. As I mentioned just a second ago, the primary result that we are looking for from the eigenvalue problem, initially at least, is the natural frequency. It tells us a lot about the structure. We are often interested in whether this natural frequency coincides with some of the frequency spectrum intervals that we know for the external loading. So it's often a good idea to initially determine the natural frequency. However, the eigenvector actually contains a lot of valuable information. And next lecture, we will actually use the properties of these eigenvectors to set up a solution strategy to actually find the full time response for a structure with a certain loading applied to it. And one of these main important properties of an eigenvector of the mode shapes are the so-called orthogonality conditions. So let's just go back and have a look at the eigenvalue problem, for instance the one shown here in 735. So we have the stiffness matrix minus omega squared the mass matrix, and then the mode shape vector multiplied onto the sum of these two terms, and that should be equal to 0. So a given eigensolution, omega j, uj, fulfill this equation. So we substitute in omega j on omega's place, and we introduce uj instead of u. So the eigensolution j fulfills this eigenvalue problem 735. Let's assume that we have another solution, eigensolution, omega k, uk. This of course fulfills the same equation as written in 736. So we have two eigensolutions governed by two eigenvalue problems written by the two top equations. Let's now pre-multiply the first equation by uk transposed and the next equation by u j transposed. So when we write out, let's just erase this. When we then write out these equations, we get uk transposed uj minus omega j squared uk transposed muj equal to 0. And the next equation basically becomes more or less the opposite. Almost, at least. It's almost opposite, unless for the eigenvalues, which are omega j in the top equation and omega k in the bottom equation. However, let's subtract these two. That means that the two first terms, they cancel, while the two latter terms combine into what is written here in 737, because now we have a common factor on both terms, and ukm uj is equal to uj transposed muk, because m is symmetric. So for symmetric matrix, m is equal to m transpose, and that's why these umu factors here are actually identical in these two equations. So that means we have a parenthesis as the difference between the two natural frequencies, and we have a factor uj transposed muk, and this equation must be equal to 0. So either the first factor, the parenthesis, is equal to 0, or the umu factor is equal to 0. However, if omega j is different than omega k is different from omega j, let's for instance say that omega 2 is different from omega 1. We saw that for the two-story shear frame building in the previous example. Well, then the parenthesis is definitely not equal to 0, and therefore this factor, this product, must be equal to 0. And it tells us that one mode shape pre-multiplied to the mass matrix multiplied by another mode shape gives us, or vanishes, gives us 0. We can actually repeat this from the top, where we, instead of having these two equations, we rewrite these equations by dividing the first equation with 1 divided by omega j squared, and the next equation by omega k squared. And it means that these equations can be written as uk transposed 1 divided by omega j squared k minus m uj, and the next equation will be uj transposed 1 divided by omega k squared k minus m u, sorry, that was too violent, k equal to 0. And suddenly, when we subtract these two equations, we get equation 739, shown here. And now we have a similar argument as before, just with the stiffness matrix instead of the mass matrix. So we actually have, from the first condition, an orthogonality relation for mass, and from the second condition, an orthogonality condition for stiffness. So what we have in both cases is that mode shapes actually are orthogonal to each other in terms of mass and in terms of stiffness. And that's an important mathematical property that we're going to use next time to actually set up a fairly simple solution procedure for dynamic systems. The orthogonality relations on the previous slide introduced conditions when j and k were different integers. What about the case in which they are the same integers? So let's just go back, and we could take the expression 737 and write that again. So we have omega, was it k or j first? Not that it really matters. Omega j minus omega k squared, and then we have u j m u k equal to 0. So let's assume that these two omegas are the same. In that case, this equation is satisfied by default, independent of the choice of UMU. So we can actually choose this value freely, and we can calculate it. And that is done to identify or to calculate the modal mass. So let's calculate uj transpose m uj. That gives us a scalar value, and this is for non-vanishing u a finite value. And we introduce this as m, j, and it's referred to as the modal mass. We actually considered the modal mass already in lecture number 1, where we had the vibratory mass of a single degree of freedom system. Typically we could estimate this by static shape functions, but in this case we actually have the exact solution to the vibratory mass. That's the modal mass, because the mode shape vector uj is obtained from the consistent or the exact eigenvalue problem. Similarly, we have an expression for the modal stiffness, because this expression up here we could also write as 1 divided by omega j squared minus divided by omega k squared, and we have uj k uk equal to 0. Again, when these two omegas in the parentheses are the same, the parenthesis factor vanishes, and that means that this equation up here is by default satisfied. Again, we can choose the second factor, that's uj transpose k uj. We can choose this as a value, and we identify it as, I'll try again, as modal stiffness. So in MATLAB, when we calculate our mode shape vectors by the generalized eigenvalue problem, it typically normalizes modal mass to unity. And that's obviously not the vibratory mass that we considered in the previous example. So what is important for you when you want to use the modal mass as the effective mass of a single degree of freedom system is that you, let's just assume you have a cantilever beam and you solve your eigenvalue problem, and this is your mode shape vector. So this one is uj. You need to normalize the maximum deflection to 1. So max deflection should be equal to 1, and then mj is the vibratory mass that we can use to actually do a single degree of freedom analysis. The stiffness is given by omega j squared mj, and for unit modal mass it gives this nice relation, but if we have an actual vibratory mass where we have normalized max deflection to unity, you should actually be able to reproduce the modal stiffness as something you could use in a single degree of freedom analysis. The orthogonality conditions can now actually be written in extremely compact form. So we have, for instance, for the modal mass, we have uj transpose times m times uk. That is equal to the modal mass times what we refer to as the Kronecker delta, and the Kronecker delta is equal to unity when the two indexes are the same, and it becomes 0 when the indices are different. So it is a tensor version of what we in 2D refer to as the identity matrix. I will here at the end briefly go through the example with a vibrating cable, where we assume a lumped mass matrix. On the figure we have the cable. It has length L, and it is divided into n plus 1, actually n plus 2 nodes with n plus 1 elements, but because we constrain the first, the 0th dove and the n plus 1 dove, we end up with a system of n times n matrices, as we covered in the previous lecture on the finite element analysis. And you immediately see the lumped structure of the mass matrix because it is enforced to be diagonal, and the nodal masses M are contained as a factor to the mass matrix. The individual stiffness components to the stiffness matrix are then obtained by the tension force divided by the element length. So M and K are given in 746 for typical cable element or finite element model for a taut cable. So we discretize the cable into n nodes. That means we can set up an n by n eigenvalue problem. You immediately see that this is written as the 1 divided by k times the stiffness matrix minus omega squared, and then we have m divided by k and the lumped structure of the mass matrix. And this one here contains 2's and minus 1's, whereas this one becomes 1 divided by omega squared, omega 0 squared, so that we get a normalized eigenvalue as omega squared divided by omega 0 squared. Just to normalize things, introducing the reference frequency previously considered for the 2-DOF shear frame structure. Push the button, find the eigenvalue, find the eigensolutions. That means the natural frequencies and the mode shape vectors. Here I have plotted the first 3 natural frequencies for a system with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. That means 9 free nodes. And you can see that the first mode shape becomes the classical single sign or half sign with a single deflection without any zero crossings, while the next, or the second mode shape, is given by the pluses with a single crossing at the intermediate node, while this third shape then has 2 crossings of equilibrium at these intersection points. What you should see is that while the first vibration mode is fairly smooth, already the second and the third will have some corners. Let's have a look at the third mode here, where you have this sharp corner with linear interpolation in both elements. That means we start to get small errors in our solution relative to the analytical solution that we have from separation of variables for the wave equation. Now the way to solve this is that we initially assume the mode shapes. So we simply guess a form of the mode shapes given by a sine function, where J and R denote respectively the node number, and they rhyme the mode number. So when we substitute this into the eigenvalue problem, we will, for any of the rows, find a solution of this form, where J simply comes from the different degrees of freedom in the vector U. That means I plug in my science solution into this generic expression representing any row in my cable model. Then I utilize a fairly relevant relation between the difference between 2 sine functions. It can be written as a factor of cosines and sines, where we have the sum and the difference between the arguments. That means that the generic equation, which can be written in this form here, will have a sine function as a common factor, and then the difference between 2 cosines. And the difference between 2 cosines can again be written as a product between sines, and that means our generic equation that we have from our eigenvalue problem can be written as a normalized sine function squared times the amplitude of our degrees of freedom. If we take this expression and substitute it back, we will actually be able to find an expression for the eigenvalue omega r, where r is equal to the number of mode that we are looking for. The interesting part here is of course that we would like to find the value for omega r, find omega 1, omega 2, omega 3, but also to compare with the exact frequency solution that we actually know from a taut cable, just to indicate to us what does it mean to actually solve a discretized problem. And we had some of this in the last lecture as well. We substitute in omega 0 and find this expression for the natural frequencies obtained from the eigenvalue for our finite element cable model. We have 9 nodes, 10 elements. So let's have a look at the mode numbers. So when we plot these, we actually follow a trajectory in the curve that is not linearly. And we know from the continuous cable solution, the exact solution, that we should have proportionality with R. However, in the beginning, there seems to be exactly this proportionality, whereas for the higher modes, we seem to have this branching off. So again, the rule of thumb is that for the lower half modes, the finite element solution is typically okay, whereas the higher half simply have errors. So those you cannot trust. Let's have a look if we can compare the low frequency solutions. So this is our full solution with the full sine function. If R is much smaller than n, then we have a very small argument. And for a very small argument, the sine function is approximately equal to the argument. That means we get this solution here. And then we can take n plus 1 and multiply onto the function underneath the square root, whereby n plus 1 times n becomes the total cable length, leaving us with this square root here. And that's directly comparable with the exact solution for the continuous cable model. So it approximates the strain or taut cable with very good accuracy for the lowest few modes. That means for R much less than n. Let's go back a little bit more than 100 years and revisit Lord Rayleigh. The idea of Rayleigh's quotient is an pedestrian way of actually estimating the lowest natural frequency, basically any natural frequency, but it's typically used for the lowest natural frequency. Let's have a look at the eigenvalue problem and try to derive the theory based on this. So we take the eigenvalue problem and we pre-multiply it by the mode shape transposed. So that means we get a solution uj transposed kuj minus omega j squared uj transposed m uj equal to 0. So we isolate omega j squared, and that provides us with this expression here within the blue box. And we realize that we have a modal stiffness as uj transposed kuj, and we have the modal mass, similar form for the mass matrix, and those we can introduce to get the final expression here. So any natural frequency squared is equal to its modal stiffness divided by its modal mass. So Rayleigh's quotient simply generalizes the well-known expression that we have from a single degree of freedom system to modes for a multi-degree of freedom system. Now Rayleigh's quotient is effective if you don't want to solve the full eigenvalue problem. Let's assume that you simply guess a shape. That could actually be, for instance, a static deflection shape that we had to find the modal mass and the modal stiffness in one of the first lectures. So you could take a cantilever beam, you could apply a load P, solve your static problem that you know from your first semester structural mechanics course, and you can actually find tip deflection here and some kind of shape function of x, and you can convert that into a vector u. Now you can also solve the static problem in your finite element code to find u. You simply guess or assume a certain shape. It's not the correct shape, it's just a guess. And you stick that into Rayleigh's quotient and you calculate such an omega r squared. You haven't solved an eigenvalue problem. You've maybe solved a static problem, but you haven't solved an eigenvalue problem. Now, is this a good guess? Depends, of course, on the quality of it. And can we say something general about how this behaves compared to the exact solution? And the idea is that this guess can be expressed theoretically by the correct vibration shapes with certain factors, and I'm pretty sure this should be a factor 2 now that I look at it, so that we can make a linear combination of our correct mode shapes with these coordinates. We call them modal coordinates. The nates are j. So we take this representation and we plug in to both the denominator in the bottom and the numerator of this fraction, and it turns out, we'll see that more greater detail next time, that it can be written as the sum of modal stiffness times deflection squared in the numerator and modal mass times deflection squared in the denominator. If we then introduce the modal frequency, let's say by the stiffness in the numerator, we see that all the terms will have a common factor. That means we can take that outside a parenthesis in the numerator, and what we will have inside would be the ratio between natural frequencies if we isolate the first natural frequency outside the summation. Now, if we have isolated omega 1, then this parenthesis squared will always be larger than unity. And that means that the correct first mode natural frequency will always be smaller than the first mode Rayleigh frequency. So it actually represents a lower bound. And this is where we should be careful, because we are looking for omega j's less than, again, 5 Hertz for our pedestrian bridge. But if we use the Rayleigh quotient, we cannot be sure that although omega r is larger than 5, we cannot be sure whether omega 1 is as well larger than 5 Hertz, simply because of the inequality. But experienced engineers, structural dynamicists, they know what type of shape one can use to actually get fairly good approximations. So Rayleigh's quotient is in many cases a strong practical tool to get first estimates of the natural frequency without actually solving the full finite element eigenvalue problem. The summary I will leave to you, and thank you for today. And next week we'll have a look at how modal analysis works in practice. Thank you.